Module 2, Session 2. Session 2 will cover Learning Outcome 3.2.2, Circle Theorems, Part 1. Learning Outcome 3.2.2, State and apply the theorems of circles. Now that you have equipped your students, it's time to move on to the major section in this level 4 geometry, which is the circle geometry. Teaching tip. It is important for students to know all of the circle theorems off by heart. This is the only way for them to use the theorems effectively. Test the students on their knowledge of the theorems and work through examples. Students don't need to prove the theorems. Work in groups to see what you remember about the circle theorems and how to teach them. Make a list of all the theorems. Discuss any problems that come up for you as lecturers or for your students in this section. In this module, we will cover the first 4 circle theorems. The module that follows will cover the remaining 5 circle theorems. Before we start on the theorems themselves, it is important to revise circle terminology with students. Circumference, the distance measured around the outside of a circle. Radius, a line from the center of a circle to the circumference. Diameter, a line through the center of a circle that cuts the circle in half, creating 2 semicircles. Sector, a slice of the circle between 2 radii and the arc between them. Tangent, a line that touches the circle at one point, the point of contact, only. Chord, a line joining 2 points on the circumference of a circle, creating 2 segments. Segment, the region bounded by a chord and the arc subtended by the chord. A chord will form 2 segments. The smaller segment is called the minor segment, and the bigger one, the major segment. Arc, a section of the circumference of a circle. The shorter arc is called the minor arc, and the longer arc is called the major arc. An important concept in circle geometry is a subtended angle. Subtend means to hold or contain an angle. In this diagram, the minor arc AB subtends an angle at the circumference and at the center of the circle. Another important term to know is the word concyclic. If points are concyclic, it means they all lie on the circumference of the same circle. Lecturers and students find it useful to organize the circle theorems into groups to make the curriculum more manageable. We can make the following groups: the general circle theorems, the cyclic quadrilateral theorems, and the tangent theorems. We are going to start by working through the general circle theorems and their converses now. There are 7, including the converses. Theorem 1 and its converse. Theorem 2. Theorem 3 and converse. Theorem 4 and converse. It is very important to note that we are numbering these theorems this way for the support package to make things easier to explain, but students should never use theorem numbers as reasons when doing problems. Different lecturers and textbooks will order and number theorems differently. Students must know the proper reason that belongs to each theorem. Theorem 1. If a line is drawn from the center of a circle perpendicular to a chord, it bisects the chord. So in this diagram, if OF is perpendicular to AB, then AF is equal to FB. When students give this theorem as a reason, they should abbreviate it as perpendicular line from center bisects chord. And the converse states that if a line is drawn from the center of a circle to the midpoint of a chord, then that line is perpendicular to the chord. Thus, if AF equals FB, then OF is perpendicular to AB. This can be abbreviated as midpoint chord perpendicular. Let's apply this theorem in an activity. Solve this on your own. Here's a video showing the solution.
Let's consider the following example. The question is as follows. Calculate the length of AB, of which OE is equal to 40 millimeters and CE is equal to 10 millimeters. The first and most important thing is to record that information onto the sketch. If we look at this diagram, you will agree with me that OE is a radius because it is the point from the center to the circumference of the circle. Therefore, I can make a note here in stating that the radius OE is equal to 40 millimeters. Then CE, that small portion there, I can indicate there 10 millimeters. Now, if you're looking at this diagram, they want us to calculate the length of AB. One thing to note here, because OE is perpendicular to AB, it means that AC will be equal to BC. And that is where we are at this stage. But we cannot go any further with this calculations unless we do some form of a construction. And the construction that I will do is I'm going to join point A and point O. In other words, now my focus will then be on triangle AOC, which is a right-angled triangle. At this stage, I have the value of OE, which is 40 millimeters. That means in that instance there, OA is also a radius because it is the point from the center to the circumference. So I can even indicate there that that will be equal to 40. Now, if I look at this right-angled triangle, the side that I need to calculate here is OC. Because once I can calculate OC, then obviously by means of Pythagoras, I will be able to calculate AC. And once I got AC, then obviously I need to double AC in order to get AB. So that was just a short description of the procedure. Now let's start with solving this problem. From my given information, OE is 40 and CE is 10, which means I can then calculate OC, and that will be my first statement. OC is equal to radius OE minus CE. And if I substitute, OE is 40 minus CE is 10. Therefore, OC will give me 30 millimeters. And now I can write in there 30 millimeters. What do we need to calculate here? We need to calculate AC, which is one of the right-angled sides. And if you need to calculate according to Pythagoras, why do we need Pythagoras? Because it is a right-angled triangle. Two sides are given, meaning that I need to find the value of AC, which is one of the right-angled sides. Therefore, I will subtract that from my hypotenuse. So, according to Pythagoras, AC squared is equal to AO squared, which is my hypotenuse, minus, obviously, OC squared. Now let's solve AC. So much straight away, then just substitute afterwards. AC will therefore be equal to the square root of AO, which is 40 squared, minus OC, which is 30 squared. And if I use my calculator, then I will get a value of 26,458, very important, millimeters, because it is given in millimeters. Once I got AC, now only then I can calculate AB. AB will be equal to 2 times AC. Right? That is 2 times that 26,458, and AB therefore will be equal to 52,916 millimeters. Now, let's just look at the problem again. AC squared equals to AO squared minus OC squared. The reason I have applied there the theorem of Pythagoras. Why? Because it is a right angle triangle. And then AB is equal to 2AC. Why? Because the reason here is OC or OE is perpendicular. You can see there the 90 degrees tells me it's perpendicular to chord AB. And that implies that AC will be equal to BC.
Theorem 2. The angle subtended by an arc at the center of a circle is twice the size of the angle it subtends at any point on the circumference of the circle. Angle AOB is equal to 2 times the angle ACB. To give this theorem as a reason, write it like this. Angle at center equals 2 times angle on circle. Let's watch a video showing a lecturer working through an example applying this theorem.
The following example, we need to find the value of ACB. First of all, you can all see that ACB is an angle at the circumference of the circle. Right. Now we need to look at what information do they provide for me in order to find ACB. And is that information linked to ACB? Angle at circumference, you can see angle at center is given. So immediately we keep in mind we will be able to apply angle at center equals to 2 times angle at circumference. But first of all, they have provided point O, and they have provided us with the value of the reflex angle of point O, which is 210. The very first thing that we need to calculate here is we need to find the value of the obtuse angle of BOA. Because if we can find the value of the obtuse angle of BOA, then obviously BCA will then obviously just be half of that. So let's find the value of the obtuse angle BOA. It's very important that we need to be specific here. We cannot just say BOA because BOA consists of 2 angles. The one is the reflex one and the other one is the obtuse one. And that's why we will be specific by stating obtuse. BOA. And that will be equal to 360 degrees minus 210 degrees, and the obtuse angle there will be equal to 150 degrees. What was the reason? Angles around point O. Once we got that, now obviously we can find angle BOB. BCA. If you look at, now we have the obtuse angle, which is the center angle, and now we need to find this angle at the circumference. So BCA will be equal to obtuse BOA divided by 2. It's going to be half of it. Which will be equal to 150 degrees divided by 2, and therefore BCA is 75 degrees. What is the reason here? Angle at center equals 2 times angle at circumference, CRUCM. And that is the question.
Theorem 3. If an angle at a point on the circumference of a circle is subtended by a diameter of the circle, the angle is a right angle. So in this diagram, if AB is the diameter, angle ACB equals 90 degrees. We can abbreviate this as angle in semicircle. The converse of this theorem states that if an angle at a point on the circumference of a circle is a right angle subtended by a chord, the chord is a diameter. In our diagram, if angle ACB equals 90 degrees, then chord AB is the diameter. We can abbreviate this as chord subtends 90 degrees. Let's apply Theorem 3. Work through this problem quickly on your own. Let's watch a lecturer going through the solution.
Let's consider this example. Now, what is very important here is people, as a good practice, as they give the information, fill it in on the diagram so that you have a complete diagram with information, and from there you'll be able to see what to do. They said BD is equal to 120. BD is equal to 120 millimeters. In other words, that is your diameter. Is that correct? Which means that OD is the radius, OB is the radius. So in other words, if BD in total equals to 120, it means that that will be 60 and that will be 60. And if you add it up, that is what that 120 means. Any comments? Don't think we will have any questions. Then OC, that is, you can see from the center to the point, is perpendicular to AC. What does that mean? That means that AC is equal to BC. In other words, when you analyze that, it means that. And OC, you can see here, OC is equal to 40. So we indicate 40. And now immediately we identify, before I even look at the question, you can immediately see here, you identify obviously right angle triangle BCO. You can immediately, with that information given, determine the value of BC. And obviously, by looking at your question there, they want AB, so you're just going to multiply it by 2. So in other words, let's start solving this problem. First thing is to note is to identify the triangle. So we're going to start with a statement by saying in triangle, I'm focusing on BOC. This is a right angle triangle. I need to find the value of one of the right angled sides, so I will subtract once again. So we're going to say, okay, BC squared is equal to my hypotenuse, OB squared, minus my right angle side, OC squared. Why? Theorem of Pythagoras. We've seen, now let's make BC the subject. BC will therefore be equal to the square root of OB squared minus OC squared. And now we substitute, that's the next step. OB squared, 60 squared, minus 40 squared. And if you punch that into your calculator, you will get a value of 44,72. And that is given in millimeters. Now we got BC, so then we can find AB. This was number A. Right, obviously, AB will be equal to 2 times BC. Why? What's the reason why it's 2 times? Because it is given that OC is perpendicular to AB, and that implies that AC is equal to BC. And now we just substitute 2 times 44,72, and your answer for AB will be 89,44 millimeters. Now let's look at the second part, B. They want the value of angle A. Now let's go back. By looking at this diagram here, gentlemen and ladies, BD is your diameter, and angle A is subtended by the diameter. And any angle that's subtended by the diameter is equal to 90 degrees. Therefore, angle A will be equal to 90 degrees. Now, here you can write it in any way. You can say angle in a semicircle, or you can say angle subtended by the diameter. Let's say angle in a semicircle. Angle in semicircle.
Theorem 4. Angles subtended by the same arc in the same segment of a circle are equal. In this diagram, both angle C and angle D are subtended by the same arc AB. So, angle C is equal to angle D. This should be abbreviated as angles in same segment. The converse of Theorem 4 states that if a line that joins 2 points subtends equal angles at 2 other points on the same side of the line, all 4 points are concyclic. In this diagram, AB subtends angle C and angle D, and these angles are equal to each other. Therefore, A, B, C, and D are concyclic. Abbreviate this as line segment subtends equal angles. Let's watch a video showing a lecturer working through an example applying this theorem.
In this diagram, O is the center of the circle, and O2 is equal to 250 degrees. So let us fill in O2 on the circle. It's going to be the reflex angle, and that is equal to 250 degrees which is equal to angle O2. That's given. Immediately, by looking at this diagram and considering point O, we can then find this angle here, which will be equal to 360 minus 250, and that's going to give you 110 degrees. And immediately by considering this, it means that DEB will be equal to half of that, which will be equal to 55 degrees. But DB also subtends angle DAB, so this will also be equal to 55 degrees. I haven't looked at my question yet, people. I'm just strategizing first, and then I will look at my question because I want to illustrate a point. If that is 250 there, then obviously this angle here will be equal to half of 250, which will be equal to 125 degrees. This is now what I have deduced from just that 250 that is given. Now you people will see something that I might have answered some of the questions already here by completing this diagram without even looking at the question. Let's look at question number A. Question number A, they want BAD. Can you people see we've already solved out BAD? But now we need to write it in a proper format. How did we find BAD? Before BAD, we have found first O1. So in other words, let's work out O1 first, because we need to now get our procedure correctly. We cannot find BAD without first having O1. So the first statement that we will write there is O1 is equal to 360 degrees minus that 250 degrees. And that was equal to 110 degrees. Why? Angle around point A. Point O, not A, sorry for that. Then, BAD. BAD is equal to angle O1 over 2, which is equal to 110 over 2, and that is equal to 55 degrees. I think I just want to note here, you people have seen that I haven't used the word obtuse. The reason is because it is already labeled as O1. That's the reason why I haven't used the word obtuse, or as the case may be 51, which means it's less than 90 degrees. I haven't specified exactly what type of angle it is because it is already stated as O1. 55, why? Angle at center equals to 2 times angle at circumference. Right, we've answered the first one. Let's look at B. If you look at B, they want BED. Very nice, because can you people see that DB, that chord BD, the arc BD, not the chord, arc BD, subtends angle A as well as angle BED. So in other words, you will agree with me that BED is equal to 55 degrees. Why? Angles subtended by arc DB. You can see it clearly. Subtends that angle. It also subtends the other angle. Now let's look at C. BCD. BCD, obviously, you can see there BCD is equal to reflex angle, O2 over 2. Why? The same reason. Angle at center equals to 2 times angle at circumference, which means that's O2, you can see that's given as 250 over 2, and BCD therefore is 125 degrees. And that solves A, B, and C.
The next activity is an example of a practical investigation you could use with students in class to help them understand circle theorems. Part 1. Draw a circle. Draw chord AB. Let AB subtend angles angle C, angle D, and angle E on the same side of the chord. Measure the magnitudes of the angles. Discuss your results. Part 2. Discuss the challenges you face teaching circle geometry and ways that you overcome these challenges. Just before we end the module, here's a summary of the theorems we have covered so far. Theorem 1. A perpendicular line segment drawn from the center bisects a chord. And its converse, if a line drawn from the center bisects a chord, it is perpendicular to the chord. Theorem 2. An angle subtended at the center is twice an angle subtended by the same arc at the circumference. Theorem 3. If an angle at a point on the circumference of a circle is subtended by a diameter of the circle, the angle is a right angle. And its converse, if a chord subtends an angle of 90 degrees on the circumference, then the chord is a diameter of the circle. Theorem 4. Angles on the circumference in the same segment subtended by the same arc are equal. And its converse, if a line segment subtends equal angles, then the endpoints of the line segment and the vertices of the angles are all concyclic. Remember to encourage students to memorize the circle theorems. Keep testing students on them. Remember to encourage students to memorize the circle theorems. Keep testing students on them. This brings us to the close of the module. We will cover the rest of the circle theorems in Module 3.